welcome everyone. We're going to go ahead and get started. And before we do that, I would like to have a moment of silence for our deceased members, our deceased fellows, and our deceased founders. Okay, thank you for that. So welcome to day 2 of the Nsbp 2021 Annual Nsbp Conference. I would like to remind you all to watch our welcome videos. We have a really dope video from the Nsbp current e-board and current student council. We have a welcome video from Brookhaven National Lab, and we have one from Associated Universities Incorporated. So Cora, would you mind for 1 second stopping your share so that I can share something?
Absolutely.
Okay, so give me a minute. So like I said, we have our conference partners, Brookhaven and AUI. We also have our conference co-sponsors. We have Corning, NRAO, NASA Goddard, and now Optica, which is formerly OSA. We have our gold sponsors are Corning, NRAO, and NASA, and Optica is our silver sponsor. And we also have our bronze sponsor, Facility for Rare Isotope Beams, Morgan State University, and the University of Notre Dame. So I would like to recognize and thank all of our sponsors and co-sponsors. And we would also like to thank our 35+ exhibitors. I personally can say that visiting exhibiting booths has led to many, many opportunities. So thank you to our exhibitors. And I would like to also remind all of our eligible members that you can cast your online vote for the Nsbp elections, which is also very important. So at this time, we'll now have our Nsbp President, Dr. Stefan Alexander. He has personally, for me, been a very huge inspiration. He has affected the infrastructure within this organization greatly. He has strengthened partnerships, enhanced partnerships, created partnerships that have led to many amazing programs since I've been on the student council, including the Simons Foundation internship, which be sure to check out those presentations because awesome research being done there. And also our mentoring program with the Harlem Gallery of Science, for which I was a mentor. So Dr. Alexander, you now can say your piece.
Well, soon to be Dr. Price, because congratulations on admissions to the PhD program. You know, I'm putting my bets. I'm going to make a bet to all members who are here. My bet is Elon Price one day will be president of NSB in her future. And we look forward to that because you are truly one of our gems, great leader. And I am just so proud. We're so proud of you. And, you know, that's all I can say. You just made my day. And so it gives me great pleasure to introduce our second plenary speaker. And I just want to jump in and just give a formal introduction, even though I know she doesn't like those kind of things. Let's say I met Dr. Dvorkin when I was on sabbatical at Princeton. And I remember being like, you know, I think I was the first African-American, you know, visiting professor in many years, or if not ever. And I can just say personally, Cara was one of the people when she was a postdoc that really put a hand out of fellowship and collegiality, and I remember that. And, you know, she is now an NSBP member. She's one of ours. So Dr. Cara Dvorkin is an associate professor in the Department of Physics at Harvard University. She's a theoretical cosmologist and has made theoretical contributions to the study of dark matter, focusing on a broad range of observational probes. She has pushed the frontiers of dark matter using the cosmic microwave background and large-scale structured data. She has also pioneered the use of machine learning techniques to find dark matter subhalos in gravitational lensing systems, and actually cites my papers. Dvorkin is the Harvard representative of the newly NSF-funded Institute for Artificial Intelligence and Fundamental Interactions Board. She has also been awarded the 2019 Department of Energy Early Career Award and has been named the 2018 Scientist of the Year by the Harvard Foundation for salient contributions to physics, cosmology, and STEM education. She's also been awarded the Radcliffe Institute Fellowship and a Schutze Professorship at the Radcliffe Institute. In 2012, she was given the Martin Beat Block Award, awarded to the best young physicist by the Aspen Center for Physics. And with all those things, and all those accolades, she remains as one of the most humble, down-to-earth, approachable, and someone that has supported NSBP and NSBP members, not with words, but with actions. And on that note, Dr. Dvorkin, the stage is yours. Welcome.
Thank you. Thank you very much. Thank you very much for the invitation, really, and the very kind introduction, Stefan. And I hope everyone is doing well in these very trying times that we are still living through. I'm happy to see some familiar faces, at least virtually, hopefully in person soon. And really, it is my honor to be speaking here today. So what I will do is I will tell you about some of our efforts with my research group to unlock dark matter physics out of astrophysical data sets. So let me get started. Here's where we stand in cosmology today. We have a standard model of cosmology known as lambda CDM. And this model has been extremely successful on cosmological scales among a wide array of different observables, from the cosmic microwave background, temperature, and polarization fluctuations, to the clustering of matter and measurements of the expansion history of the universe. So here I'm showing you the matter power spectrum. Do you see my cursor? Yes. Here I'm showing you the matter power spectrum as a function of wave number. You can see that it is a log-log plot, and it covers 4 orders of magnitude on each of these axes. The black line here shows the predictions of our lambda CDM standard model of cosmology. And each of these data points is a measurement interpreted within the context of this model as a measurement of the power spectrum. And what's interesting about this figure is that it's spanning 14 billion years of history. It's spanning 4 orders of magnitude in length scales and a wide variety of cosmological probes. And we can see how the lambda CDM model fits them all beautifully. So in the past few decades, we have measured the large-scale structure of the universe very accurately with many different probes, the CMB and galaxy surveys, among others. And this has allowed us over here to put precision level limits on different kinds of dark matter scenarios. On smaller scales here, however, there is a lot of structure, but it is not as well understood. Furthermore, many dark matter scenarios that agree at large scales by construction show differences at small scales. So observations at small scales provide fertile grounds for testing different dark matter theories. And this is the idea that I want to exploit today. So because we know structure formation is hierarchical, we expect an abundance of structure within dark matter halos. In particular, in the cold dark matter scenario, for example, we expect a high abundance of substructure compared to other dark matter theories. This can be seen in this plot over here that I took from one of Andrei Kravtsov's papers, where we see the predicted dark matter density for a Milky Way size halo from a high resolution embodied simulation in this case. And we can see that there is a lot of structure, see, within the halo. And one of the things that we have been analyzing with my group is how to tie these small structures to dark matter theories. Moreover, we know that these structures exist because we have actually observed them. Here on the right, we can see a map from last year from the DES collaboration, the Dark Energy Survey collaboration, of observed Milky Way satellite galaxies, meaning small galaxies that are virially bound to the Milky Way. And so in this talk, I will be focusing on the CDM part of our lambda CDM model. I will tell you about some of the research that we have been doing with my group at Harvard to provide an understanding to the question, what is the particle nature of dark matter? which constitutes approximately 84% of all matter in the universe. 84% of all matter in the universe, and we still don't know what it is. So as an example of the effect of different dark matter models on subgalactic scales, I'm showing here two different projected dark matter densities. One coming from an embodied simulation in a CDM scenario on the left, and on the right, I show a simulation with the same initial condition, but including some exotic dark matter microphysics that results in dark matter clumps, which are more susceptible to tidal stripping. You can already see by eye here that there is a lot more structure in the CDM model than in this exotic dark matter scenario. And this is just an example to illustrate really the fact that exotic dark matter physics can lead to interesting phenomenology that is observably different from CDM on small scales. And so the idea that I want to show you is will be to probe dark matter fluctuations on small scales. And by this, I mean, it's subjective when I say small scales, but by this, I mean kiloparsec scales, to satisfy, to basically to corroborate or falsify the CDM paradigm. So our goal is to map the distribution of dark matter on small scales in halos of galaxies. And our tool for this will be strong gravitational lensing. So in case there are students in the audience, let me give you a review in one slide of gravitational lensing, okay? So basically we will have a background source at some high redshift at a far distance, which will be a galaxy in our case. And there will be a foreground galaxy between us and the background source that deflects the light because of its gravitational field. So from our perspective, we are here in the telescopes, we can see extended arcs, see? And so the idea will be to use these images of arcs to see if the lensing galaxy, this guy over here, is clumpy or smooth. And so one can map an image back to the source plane by a deflection angle field, which is the gradient of the gravitational potential of the main galaxy acting as a lens. So this is the idea of strong gravitational lensing. And the idea to look for subhalos has been suggested about 20 years ago by Mao and Schneider. And the idea is that substructure in the halos of galaxies, okay, I will call substructure the small clumps of matter in the halos of the big galaxies. And these will locally perturb lens images. So by looking at the residual between the image predicted by modeling the lens galaxy as a smooth mass and what is actually observed, we can infer the presence of subhalos. And I will call subhalos the substructure that is in the halo of this galaxy. The advantage relative to other methods for detecting dark matter is that in this case, we do not need to assume a specific coupling between the standard model and the dark matter, in contrast to, for example, direct and indirect detection experiments or colliders. And so in this sense, I like to say that we are model independent. We just rely on gravity. Another main advantage of the technique I will tell you about is that, especially in the second part of this talk, is that I will be focusing on the lowest mass subhalos, which we believe are largely devoid of stars. So detecting them with a gravitational technique is really the only possibility that we have, since these subhalos cannot be seen directly. They don't emit light. So the lens galaxy will have small scale structure, and this will cause a deflection as the light from the source crosses the lens. If you don't have superpower in your eyes, you will not be able to see any difference between this unperturbed image and this perturbed image. So let me show you the difference. These are the image residuals once we subtract the smooth model of the lens. So here you can see that we are talking about a percent level effect, you see, on the surface brightness map of these lens galaxies. And these variations, these percent level variations, are caused by having substructure in the lens galaxies. So with my group, we have been doing work in this arena following basically two different and complementary approaches. The first approach is what I call the direct detection approach, where our goal is to resolve individual, more massive perturbers and from there infer their properties. The second approach is the statistical detection approach. That's how we call it, where we want to marginalize over individual subhalo properties to learn about the subhalo population characteristics. And so here we exploit the fact that we expect the subhalo mass function to be steep. This is the expectation that we have a huge population of the very low mass subhalos, and we try to statistically detect their collective perturbation on images. So let me start here by talking about the direct detection approach. We will build intuition, and then we will jump to the indirect detection approach. And this is the line of time for my talk. Okay, so the quintessential method for direct detection of subhalos is known as gravitational imaging. Much like what Mao and Schneider proposed, the underlying principle is that if you have a dark clamp lying close to an imaging projection, there may be some visible distortion that you can try to reconstruct. This figure over here that I took from a paper by Simona Beghetti and collaborators from about 10 years ago, very nicely illustrates the pipeline that goes behind this. We can start from some data. In this case, it will be a strong lens galaxy. And we have to model the smooth component of the object doing the lensing, assuming that there are no dark matter clamps. And we also need to reconstruct the source. Once we have these two ingredients, we can forward model the source to obtain the smooth model image. Okay. Now, by trying to minimize the residual between the data and the smooth model image, we can ultimately reconstruct the surface mass density that gave rise to the original data set. In this particular case, we see that the reconstructed mass density, or what we call convergence field in the field, has an overdensity over here. And this was a 10 to 12 sigma claim detection of a dark matter clamp at this position in the image. You can see this reconstructed surface mass density and this overdensity over here. So this has been claimed to be a subhalo in this Nature paper. So far, using this method, there have been a few detections of subhalos in the order of 10 to the 9 solar masses from order tens of images analyzed, about 30 images analyzed. And what I want to emphasize here is that this is a very computationally expensive process, and it can take up to months to analyze a single system. So if you have tens of images to analyze, that's okay. But in the next few years, we expect tens of thousands of these lenses to become available for this type of science through the Vera Rubin Observatory, for example, formerly known as LSST, and further follow-ups. And in fact, there are already many recently discovered by the Dark Energy Survey, DES, that are waiting for follow-ups. So this is great, since the vast increase in sample sizes will provide much stronger constraints on dark matter. But obviously, it is unsustainable to take months to analyze each system when we have tens of thousands of them. So what motivated us, together with my former PhD student, Ana Díaz Rivero, was the following question. Can we automate a procedure like direct detection using convolutional neural networks, making this process much faster, circumventing the step of macro modeling? And if we understood the sensitivity of our machine learning model well enough, we could still combine detections and non-detections to probe different dark matter scenarios. So the costly step in our procedure was to simulate high fidelity strong lens images. This is an example of the individual components that went into simulating the final image. And let me say here that for this, we used a fantastic code developed by Simon Beerer, a postdoc at Stanford, known as Lenstronomy. It's open to anyone to download from the web, and it's really a very useful code. So this is an example of the individual components that went into simulating our image. We vary the macro model and the source together with the subhalo population in every image. And there are many degeneracies between these parameters. So in principle, it was not obvious at all that a network could learn something. For the source, we model it as a superposition of different clamps. We vary the ellipticity and the position of the host relative to the source. We had images with and without substructure. We convolve the image with a Gaussian point spread function, PSF, close to that of the Hubble Space Telescope, and we added Poisson noise. We also tested for correlated noise to mimic a process known as drizzling. Now, we turned the problem into a binary classification task, and we asked the question, for what subhalo masses is the network able to recognize the lens as having subhalos versus not having any? This is the binary classification task. And so in this way, we could identify promising candidates. And since most images analyzed with gravitational imaging yield non-detections, this could cut down analysis time and resources by a large factor. And our expectation was that for very low masses, the network would not be able to detect anything. But if the subhalos were massive enough, the network would be able to detect them, analogously to what happens in direct detection methods, as I showed you before. So we simulated subhalo populations, fixing the number of subhalos, also fixing the number of, fixing the fraction of mass in substructure. These two cases gave very similar results. With a very simple architecture, we found for realistic levels of noise that we could be sensitive to subhalos with masses around 10 to the 9 solar masses, comparable to the number cited in the literature for real detections, even in the presence of correlated noise. And these results are very promising since they show that we can accelerate the process of discovery by many orders of magnitude, basically from months to much less than a second once the network is trained, of course. So this was done as a proof of principle, but of course you could get even better results by further optimizing your architecture. And let me mention here that many people work on this. For example, Stefan work on this with Ivan McDonough on a paper, a different paper, but looking also for substructure with machine learning. So what we did is we then took the problem a step further and tried to cut the middleman entirely. We tried to convert the entire detection pipeline into an image segmentation task. Image segmentation is the problem of taking an image and trying to understand what the individual components that make up this image are. This was, by the way, done with my postdoc, Brian Ostiek. So to do this, we used a network architecture called UNet. UNets are networks well known for their success on image segmentation in biomedical research. The nice thing about this field of machine learning is that it gets very interdisciplinary. So we can learn from fields, for example, biomedical research that I have never thought I would learn something for that is useful for my research before. So here that we taught the network to reconstruct the convergence field. When I say convergence field, I really mean the surface mass density by classifying every single pixel in the image as belonging to the background, the main lens, or one of various subhalo mass classes. So the input was a strong lens image and the output is the probability of each class. Here I'm showing you the confusion matrices for two cases with different noise corresponding to different number of orbits with the Hubble Space Telescope. And this tells us that for a given class, this tells us what is for a given class, the type, what is the type of pixel more often predicted, what is the prediction that is more often obtained. So we see that the network struggles, for example, if you see here, we see that the network struggles to find the lower mass subhalos, and this is because the level of noise here is just above the pixel brightness changes due to the presence of these subhalos. And we provided an exact mapping in the paper that helps us understand exactly where we lose sensitivity. So we understand very well why it happens exactly here. Here, we start losing sensitivity. But we also see that it does fairly well for the higher mass subhalos, for subhalos above 10 to the 9 solar masses, which are, again, numbers comparable to the ones cited in the literature using standard methods. Moreover, we show that the network can actually find not just one subhalo at a time, as it was trained for, but in fact, it can find a lot at a time. On the left here, there is one such example, and we can now combine many of these images to place constraints on the logarithmic slope of the subhalo mass function which again can give us insight on the nature of dark matter. And this is the problem that we always have in the back of our mind. And so we can see how if we combine more and more images, of course, this reduces the error bar. And for example, with 1,000 images, we can see that we can get to 10% error bars. So this is quite exciting. We are seeing that in training many of these images and testing in many of these images, we can put constraints on the logarithmic slope of the subhalo mass function to differentiate different dark matter scenarios. Now, in fact, I became so excited about using machine learning techniques in my research that I joined forces with colleagues in various disciplines of physics and computer science at MIT, Harvard, Northeastern, and Tufts. And we recently, actually during pandemic last year, started a new NSF-funded AI center that we call IFI, which stands for Institute for Artificial Intelligence and Fundamental Interactions, where I serve as the Harvard representative at the Institute board. This is my only advertising slide. So let me say that we have our colloquia on Fridays, actually at 2 p.m. Eastern time, a little bit in about 1 hour and 20 minutes. And today, actually, my postdoc, Brian Osdiek, is giving a talk, and everyone is welcome to attend those. So if you go to this website, you can see all the information there. Okay, so let me switch gears now and go to the second part of my talk, where I will be talking about the statistical technique, where we marginalize over the individual subhalo properties to obtain population characteristics. So the actual statistical observable that I will be talking about is called the convergence power spectrum. And the convergence, again, remember, is the surface mass density. So I will be talking about the power spectrum of this field. The convergence power spectrum is particularly attractive for the task that we have at hand because it provides a bridge between what we observe, a strong lens image, and what we want to learn something about dark matter theories. And the way this is done is by the fact that the convergence power spectrum can relate length scales, which are basically the deflection vectors on the lens plane caused by whatever is doing the lensing, to a mass scale, which is what dark matter theories are actually predicting, the halo or the subhalo mass function. So the convergence power spectrum is actually a neat bridge between the two sides of this diagram, what we observe and what we want in theory. So let's start by considering the limit in which all of the perturbers are substructured that live in the lens, what I call subhalos. And once we build intuition and we understand how different microphysical properties of dark matter get imprinted on this observable, we can move on to the much more general and complicated case of a full three-dimensional distribution of perturbers, what I will call perturber, interloper, or line of sight halo. So let me start with the subhalos. In a paper, again with Ana Diaz-Rivero and Francis Yancy Racine, a former postdoc at Harvard, who is now a professor at the University of New Mexico, we developed a general formalism to study in principle, the endpoint correlation function of the convergence field. And we started from the power spectrum, which is the easiest. If we have a lot of substructure, the perturbations will look very close to Gaussian. Basically, the central limit theorem will kick in, and most of the information should be in the power spectrum. We model the convergence field as a substructure component, see, superimposed to a smooth varying background density profile of the host over here, K0. So here the convergence field of the substructure depends on the substructure position, the mass, and the intrinsic properties of the subhalos that might determine the density profile. So we propose here a change of language, moving away from talking about subhalos, and instead we propose to talk about the correlation function of the projected density field. And so the advantage of this is that we don't need to define what we mean or don't mean by a subhalo, as it's generally done in the literature, and it's many times confusing because people have different meanings. This is very clear. This is a change of language. Here we only care about the correlation function of the projected density field. So we started from first principles. This has been done in the literature for the large-scale structure a long time ago. And since I was more familiar with this area when I started working on this, I applied the same kind of philosophy, but for smaller scales. So we describe the power spectrum in terms of a one subhalo term, analogously to what is known as the one halo term. And this arises from ensemble averaging over the spatial distribution of a single subhalo. And then we define a two subhalo term, which arises from averaging over pairs of distinct subhalos. This is again analogous to what is known as the two halo term. And so here you can see that we are taking integrals over probabilities of the mass, the intrinsic properties, and the spatial distribution within the host. So, Here is our power spectrum. I'm showing here the one subhalo term. For the remaining of the talk, I will be ignoring the two subhalo term. Ask me about it if you want at the end, if you're interested. So we can see that the power spectrum here is mainly described by three quantities. At low K, we have a plateau, a constant amplitude. Here we are probing scales that are much larger than any subhalo in the system. So at these large scales, all the subhalos are essentially point masses, and the Fourier transform of that is white noise. The amplitude depends on average abundance of substructure as well as mass moments. If we move on to smaller scales to the right, we have a turnover scale given by tidal interactions of the largest subhalos in the lens galaxy. And if we keep moving on to smaller scales, we reach an asymptotic regime where the power spectrum asymptotes to a constant power law, as you can see here. And this slope reflects the properties of the inner density profile of subhalos that you see over here. This is the density profile, and this is the inner density profile, which corresponds to this asymptotic regime over here. And this will be different for different dark matter scenarios. In particular, for an NFW profile used to describe the CDM scenario, this asymptotic slope goes as 1 over k to the 4. Now, if we have a non-trivial dark matter scenario, the density profile will change. Here we took as an example a self-interacting dark matter scenario. And it has been shown that this dark matter scenario gives rise to a chord profile, as you can see in this figure in green. Now we see that at small scales, this chord profile changes the slope, which reflects the fact that the subhalo inner density profile looks different in this model. The slope now goes as 1 over k to the 8 instead of 1 over k to the 4. So here we have a promising theoretical prediction to distinguish between different dark matter scenarios. But we can see that also, in order to distinguish the different dark matter scenarios, we need to go to very, very small scales. And I will show you in a minute how by combining redshift information, we can go to larger scales to differentiate between these different dark matter scenarios. And these are scales that can be probed with near future observations. So let me skip this slide over here in thinking about time. And so let me now briefly discuss the redshift evolution of this observable. On the left, I'm showing here the evolution as a function of redshift of the power spectrum in a CDM scenario. As we go up, we evolve in time. See that the redshift changes. And so the evolution here is quite intuitive. We see that as we evolve in time, the amplitude is increasing, and this is because we are accreting more and more substructure as time goes on. On the right, I'm showing the same thing, but for an exotic dark matter scenario, which includes a low mass cutoff in the initial power spectrum and dark matter self-interactions, which has the effect to make the subhalos less concentrated and thus more likely to be tidally disrupted. So you can see that this is reflected in the fact that the amplitude got stalled between redshift of 0.5 and 0 here, where the increase in accretion in substructure is being compensated by the fact that a lot of this substructure is being destroyed. And this reduction of the affected subhalo mass at lower redshifts leads to a net transfer of power from the larger scales to the smaller scales in the power spectrum. And you can see this as a change in the power spectrum slope for scales that are k greater than about 2 inverse kiloparsecs. So compared to CDM. And we know that these scales are accessible by near future experiments. So you can see that when we go from redshift 0.5 to 0, the slope of the power spectrum changes in comparison to CDM, because there is a net transfer of power between the larger to the smaller scales because of tidal disruption in these kind of scenarios. So we just saw that the convergence power spectrum of subhalos within lensing galaxies is a promising observable to study dark matter. However, the distances involved in strong lensing systems are vast, and we expect the relevant volume to contain line-of-sight halos that are not associated necessarily with the main lens. And so recently, in work carried out by my group, in particular, I want to emphasize 2 of my graduate students, Chan Sengul and Arthur Zhang. We developed a formalism to calculate the effect of line-of-sight halos as an effective convergence power spectrum. And now, instead of having a single lens plane at some redshift, we have any number of lens planes corresponding to the line-of-sight halos. And instead of using the vanilla lens equation, we use a recursive lens equation, which couples the angular deflections of the successive lens planes. So let me go quickly through this slide in the interest of time. By assuming that the perturbations due to the line-of-sight halos are small, we show that they can be projected onto the main lens as effective subhalos. We defined what we call effective convergence power spectrum. We show that our numerical estimates are in well agreement with simulations. And we also showed that for this particular case, we expect to have a lot more power coming from line-of-sight halos compared to subhalos. But this is a particular example, and we wanted to make a more general statement. So what we did is we studied how the relative contribution of line-of-sight halos and subhalos depend on the source and lens redshift, as well as the assumed halo and subhalo mass functions in a general way. And so to understand this, here I'm fixing the halo mass function, and I'm varying the amplitude of the subhalo mass function. Redder colors show here that the line-of-sight halos dominate, and bluer colors show that the subhalos dominate. F sub here is the fraction of halo mass in subhalos. Okay, so pretty intuitively, we see that as we increase the amount of subhalos, the colors go from red to blue, as I just told you. The question is, which of these 3 panels are we observing in practice? And we don't know exactly what the value of F sub is, but there are upper limits based on measurements of different systems. And we see that from the literature that having a substructure fraction of 2% over here is very unlikely for the mass scales that we are considering here. It is much more likely that we are in a scenario like this one over here, and meaning that the line-of-sight halos are dominating. And why is this important? Well, here I overlaid points that corresponds to the Bells and Slugs families of galaxy-galaxy lensing. These are 2 well-known high-quality sets of lensing images. You can see the Bells family is in green and the Slugs family is in yellow over here. In particular, these are sets that have been used to place constraints on dark matter. And we can see that for both sets, for a fraction of substructure that we think is more realistic, these systems are likely dominated by the halos along the line of sight. So in order to translate a measured power spectrum amplitude to a dark matter theory, it is important to understand whether the subhalos in the galaxy or the line of sight halos are the dominant contribution to the power spectrum. Otherwise, we can obtain wrong inferences about the nature of dark matter. And the fact that under many lensing configurations and reasonable subhalo population assumptions, the line of sight halos contribution dominates should be good news. at least for us, is good news because the subhalo mass function is very hard to pin down. Well, in comparison, the line of sight halos live relatively calmer lives. So how can we distinguish their effect, you may be asking? Well, if the perturbation is caused by a line of sight halo, it turns out that the different planes in the problem cause a curl component in the deflection field. And in preparation for the future, we are now applying different types of architectures, of machine learning architectures, to predict the curl in cases where we have interlopers, line of sight halos, instead of subhalos. Our results look promising so far, but I should say that this is for the case when there is no noise. And for a case with noise, we are looking into much more complicated architectures than what we have tried before. In terms of current data, and this is work in progress, we are reanalyzing systems that were previously claimed as subhalos in the literature, and our current Markov chain analysis indicates that it is likely that many of these systems are halos along the line of sight. Here's one such example that was claimed to be a subhalo in a Nature paper years ago. And these are results from a Markov chain over the parameters of the source, lens, and perturber. And we find that this system is indeed very likely to be a line of sight halo. Okay, so let me summarize what I talked about until now. So I showed you how we can use gravitational lensing to probe dark matter at kiloparsec scales, a regime which so far has remained much less tested than the larger structure in the universe. I told you about ways to enhance direct detection with machine learning techniques. In particular, I presented methods that have comparable sensitivity to traditional methods, but are orders of magnitude faster once you have trained the machine learning model, of course. I also talked about the statistical probe, the convergence power spectrum, which has the advantage that is sensitive to lower masses than direct detection, and it provides a more direct link to dark matter theories. Since our initial paper, where we introduced our formalism for computing the power spectrum and connecting it with dark matter theories, several works have computed the power spectrum in simulations, and upper limits have been placed using strong lens systems. So far, no detection has been made yet. Finally, I showed how we think that line of sight halos are the dominant contribution for galaxy-galaxy lensing, and this should be good news for our ability to say something about the nature of dark matter in an unbiased fashion. So today, we talked about how we can exploit the information on small scales to gain insights on the dark sector. But I want to emphasize that with examples of work we did with my group, that there are many more different ways that you can test the dark sector at every scale by using different cosmological observations, from the cosmic microwave background to the large-scale structure of the universe, gravitational lensing, and other tracers of the matter fluctuations. So this decade will bring a wealth of new and complementary data sets, and we will continue to exploit their complementarity and look for new ways of extracting information, and hopefully we will be able to shed even more light on the dark sector. So stay tuned.
Okay, Dr. Dvorkin, thank you so much for a very interesting, very insightful talk. At this time, we are going to accept questions from our attendees. So please submit your questions. I'll give it a second for people to type what they want to say, and then I will ask a question. But while I'm waiting for that, can I ask a little bit more about your journey here? This is some very interesting work, so I'd just like to hear a little bit more from you about your background.
My background, so I was born and raised in Argentina, a country in the south of South America. I am from Buenos Aires. Is that the type of background that you wanted?
Yes, that's great.
Okay, cool. I studied physics there. I actually, I was always inclined for either math and physics or philosophy. And at some point I thought I would pursue both at the same time, but I got consumed by physics. But I have always been very interested in both. And in 2005, I decided to do my PhD I should say in Buenos Aires. I got my degree in physics in a public university, the biggest university in Argentina, known as University of Buenos Aires. And I'm very proud to have studied there. And then in 2005, I came to the US, to University of Chicago, to do my PhD there with, my advisor was Wayne Hu, and I studied cosmology with him. And when I graduated, I went to the Institute for Advanced Study as a postdoc, where I met Stefan, as he mentioned at the beginning. I was there for 3 years, and then I went to the Center for Astrophysics at Harvard to do a postdoc that was supposed to last for 4 years, but it lasted for 1. And then I became a faculty at the physics department here.
Wow, that is an awesome, that's an awesome story. Thank you for sharing that. Could you also share while we wait for, by the way, you can submit questions in the chat or the Q&A. I'll be monitoring both. So while we wait for our attendees to submit some more questions, could you talk a little bit about outside of physics? So what kind of things do you do maybe for fun or other passions that you may have?
Yeah. So what kind of things I do for fun? These days, I don't have a lot of time, but when I do have time, I like to watch old movies that has, by old, I mean movies from the 70s or the 60s. This has been an old passion of mine since I was very little, and I used to watch Russian movies with my dad. I love watching Italian movies, French movies, all sorts of movies. I like painting, although I'm a very bad painter, but it relaxes me because it takes out my brain from where it's usually at, and I just go into, into relaxation form. And what else? I like to listen to music, in particular, as I was mentioning to Stefan, also because I know I can share this with him, I like listening to jazz. I saw a question in the chat that I think it's better for Stefan. I think the question, let's see. The question is, can you discuss your thoughts on the relationship between physics and jazz? And this is a perfect question for Stefan.
Yeah, well, that's a great question.
He has a book on that.
Yeah, no, that's a great question. And I wrote a book called The Jazz of Physics that goes into that for like 300 pages. But I think the one that really fascinates, that surprised me the most was when I started looking and studying, I'm a student of the music. I started studying John Coltrane a little bit deeper. And Coltrane did an album called Giant Steps. And then even post Giant Steps, that album, you could see some of these devices. When I say devices, I mean literally like structures or patterns that John Coltrane developed, because he was kind of like also a theorist. And what's really interesting was Coltrane, actually, anything that he can get his hands on about Albert Einstein, he would study it. His son, actually, Ravi Coltrane, actually told me this. And basically, he once confided with a theorist, David Amram, that what Einstein did for physics, he wants to do the same for music. So there's an interesting diagram that John Coltrane devised. It's called a Coltrane diagram, or a Coltrane Mandala. And if you look at it and you stare at this, it's basically this like embedded circle with where he lines out, along the surface of the circle. And then you have like clusters at every point on the circle. You can think of like, 12 equidistant points. And in every circle, at every point, there are clusters of notes. And these notes have mathematical relations that like start looking like the Fourier series, basically. And then there's symmetry transformations between them that relate all the different scales that are relevant for his jazz solos and practice. And this was based on a symmetry principle. So Coltrane really understood that where Einstein was at had to do with symmetry and invariance. And so basically giant steps actually is, right, the structure behind the improvisation. That structure is based on very deep mathematical symmetry principles that Coltrane really was inspired by Einstein. So, but it's more interesting. Obviously, there's improvisation and all this other interesting things, and how physicists actually do. A lot of us, what we do actually is we do a lot of improvisation in our creative process, as well as working within the structures that we all learn. So anyway, that's in a nutshell a little bit about the connection.
Yeah, that's very interesting stuff. Thank you, Dr. Dvorkin and Dr. Alexander, for just displaying the multifacetedness of physics and physicists. Of course, we all know that. So we're going to go ahead and get back to the questions for the talk today. So we have our first question, another question from William. Have you considered using graph neural networks as compared to UNet?
Yeah, that's a good question. In particular, for example, for curve, so I have not, I have been thinking about it. I have not incorporated graphs to this particular problem. I was thinking about it more in the context of the CMB, because it turns out to make things simpler in curve space. But it's a great question. Yeah, I would be happy to. Who asked this question? Sorry, I would be, let me see.
William Ratcliffe. Actually.
William Ratcliffe. I would be happy to talk more with you offline about it if you, and perhaps we can brainstorm about it. It would be interesting. I have graphs in my mind, but I have not applied it yet to this problem.
Okay, thank you for that answer. So we're going to go to this next question, and actually a couple people asked a similar thing, I think. So William again asked, is there any work on machine learning and testing models of gravity? And then we have, hold on, let me get the name. Marcel Howard asked, can we use machine learning to distinguish predictions of general relativity to some other theory of modified gravity?
Well, before I want to cut in, Marcel Howard is Arthur Kosowski's PhD student, Cara.
Oh, I see.
He's a young cosmology superstar in the making.
Awesome. Nice to meet you, Marcel. There have been works on that. Marcel Howard, yes, I will write down your name and I can forward you some papers on that topic. There are some works on that, on trying to distinguish modified gravity from GR. Marcel Howard.
That sounds great.
Please email me if in case you don't hear from me. Just
I'll pass your email on to Marcel. Thanks.
Yes, thank you.
All right, so our next question is from our president-elect, Hakeem Oluseyi. So this question says, how might upcoming space missions impact this work? There is GWST and Nancy Grace Roman, which has wide field capabilities.
Right, so I expect those to be able to detect more. So first we have to detect the lensing galaxies, right? Once we detect them, we need to go into them with more detail. So we need follow-up works to go and see them in more detail, but definitely these missions will help find more of them.
And then another question, might there be an application to exoplanet research? Planets and disks are essentially star halo substructure.
Yeah, there is a lot of work on the, sorry, I don't see where the question is, but if the question is related to whether we can use machine learning to for exoplanet detection, definitely, and this is being used.
Okay, thanks for that answer. So next question says, at some point you had to consider a propagation model with many lenses instead of a single lens. I may have missed it, but are you able to independently identify the locations of the lenses, or do you have to treat the spatial distribution of lenses in a statistical way? And this is from Kenna, by the way.
Great question. So this is what I was trying to say, that yes, we need to, so the line of sight halos will have different planes along the line of sight. And so how do you distinguish them, right, from a single lens, where the subhalos live, where the main galaxy lives? And this is what I was mentioning here, that the difference is that it turns out that the coupling between the different lenses gives rise to a curl component of the deflection field. And so at the moment, we're trying to study systems that have been analyzed in the literature before. This is work in progress. I should flash it, but systems that have been analyzed in the literature before to look for this curl component and try to differentiate where they are in 3D. So that's what we are doing right now.
Okay, thank you. I'm gonna, oh, wow, another question. So are there any, oh, this is from Ronald Gamble, by the way. Are there any possibilities of applying this methodology to resolving jets from blazars at point sources?
Good question. By this methodology, you mean machine learning? I'm not very familiar. I'm not very familiar in that subfield. I don't know how promising machine learning methods would be to that particular problem. So I would have to look into the literature to understand. I'm not an expert in that field. I cannot make an assessment of how promising these methods would be for that specific problem.
Okay, thank you. So we have our next question from Josh Tong. Can we observe dynamic gravitational lensing, where the lensing of a galaxy changes over time?
So if we can, the question is if we can observe the changes in time of the galaxy of the main galaxy doing the lens. Not currently. I mean, already, if that's the question, not currently with these methods that I described. Already we are having a hard time describing the lens itself. So I'm not sure if that was the question, Daniel Holmes.
Oh, he said
microlensing. Okay.
Yeah, you see it.
Okay. Yeah, sure. I mean, microlensing is being used, for example, for detecting planets.
Okay, so this is a more broad question, again, from William. He asks, what are your thoughts on the role of AI in physics? Is the curriculum keeping up?
Good. So, yeah, I think that there should definitely, this is a great question. I think that there should definitely be a more formal training of people starting, or students, faculty too, postdocs, starting to do machine learning. Because currently what is happening is that people, try to start doing machine learning coming from another field. And, if you want to start doing something fast, you go to some blog and you read how this is done and you apply it quickly. But the field is advancing very fast. It gets more complicated and people miss important points, like when is this, when are these methods applicable, when they are not applicable? How do you know if the method is just telling you something about the particular simulation that you are studying, or is telling you something generic? So it's relatively easy to use a machine learning methods to a particular problem, but it's not so easy to understand whether you're truly learning something with this method. So I think in that sense, the curricula at this moment is not really keeping up, in the sense that there are some attempts to having some master's degrees here and there. In general, mostly at more elite universities, they have some master's degree on data science, but it would be nice to actually have these more widely spread and more of a formal thing for everyone wanting to do machine learning. Because I think at this point, the procedure of going directly to a blog and picking up some method and applying it, it came to an end, unless you want to play with machine learning. But if we are really trying to do science, we should learn what are the relevant tests. A lot of things that are happening in this field, for example, is that people apply machine learning techniques to, there is no domain adaptation. There is some machine learning technique that gives some result with some expensive simulation, but it's not clear if this is, generalizable or not, or if this is true for any other simulation. So there is a long way to go. I don't think that curricula are keeping up.
Thank you for that perspective. It's very insightful. I never thought much about that before, but I know the impact that machine learning and neural networks and all of that is having in physics, and I know the potential that it has to be extremely useful. So I just kind of learned about it from talks like this, and reading physics magazines. Definitely not something that I've necessarily seen in my coursework yet. So I think that integrating that into curriculum could take physics to certainly an evolved level.
Mm-hmm.
So at this time, I'm gonna just give a little pause for any more questions that we have for Dr. Dvorkin today. So I'll let you can submit again to the chat or the question and answer. So Dr. Dvorkin, I'm going to give you the opportunity, because we have some time here, to share anything else that you would like about your work, about anything, honestly. The platform is still yours, so just going to give you that opportunity.
Well, how much time do we have?
I mean, you can talk about your future work as well. Any directions that you're planning to take this?
Yeah, well, so let me know.
Got about 20 minutes.
Of time, but just to mention, perhaps I didn't go into detail in this, but what I mentioned in this talk is really the smaller scales possible that we have been targeting to understand the dark sector. But with my group, we are trying to understand the dark sector at many different scales. So one thing that we have been very interested in, for example, is light but massive radix. These are particles that decoupled early on, so became non-relativistic before today. So they have a contribution to the radiation at the CMB times, but behave as dark matter today. And we think that there could be particles beyond the standard model that have this property. And we pointed out a way to look for them in this series of papers over here. And we actually put constraints on different types of particles, scalar particles, Weyl vectors, Weyl fermions, vectors, and Dirac fermions. So that's something that we have also been pursuing as part of the dark sector, using the CMB and the large scale structure to test for physics beyond the standard model.
Okay, thank you for that little bit of extra insight. So I'm going to turn it over to Dr. Rock.
Hello. Dr. Dvorkin, thank you very much for that very wonderful talk, engaging. And the questioning seemed to take us a little deeper in a different way. It seems like, so it means you must be, your work must be definitely on the bullseye. Because if everything else is circling around it, then it means you must be on point in what's going on. So again, we thank you very much for that very engaging talk.
Thank you for the invitation.
And to know that you have such a great background. You said, when I heard you say that you were interested in getting your PhD since you were about 5 years old.
No, not in getting a PhD. Did I say that?
Oh, okay.
No.
Okay.
No, not at all. What I mentioned is that when I have always had this interest in philosophy. That's what I mentioned.
Okay.
Certainly not since I was 5. Yeah, but when I was in high school, I thought I would study math and philosophy. So
awesome.
Somehow studying cosmology is like I joined the two.
Okay. Oh, mine. Okay. I guess I heard that number 5 and it just kind of stuck in my head.
No.
I have a question for Dr. Dvorkin, Mr. Past President. Cara, so maybe I may ask you to get a little bit more kind of personal. What kind of moves you to, take interest? I know you've always been interested in sort of like, expanding access to others, but like, to get involved with Nsbp and how do you see sort of your future involvement? What kind of things would you like to do? Would you like to see happen?
Yeah, that's a good question. So obviously, look, I joined Nsbp last year when we had a lot of discussions about the murders that happened. But I should say, I don't feel that I can represent really minorities. I'm a woman and I'm from Latin America, but it's not at all as badly represented as Black physicists. So I think that I am trying to make connections between, I thought I could make connections between Nsbp, the National Society of Black Physicists, and the Latin American community by being,
nice.
By being in connection with both. But I'm not at all trying to stand as, the same type of minority as you, for example. I think I have been more privileged in that sense, but my interest, so I'm not coming as a representative of minorities, but I'm interested in opening up the doors to different to different institutions or different agrupations, also to Harvard. I mean, not necessarily to the Latin American community, but to conferences that I may hear that perhaps they are missed in Nsbp, so I would be happy to pass on this information.
Well, thank you for your continued support.
Thank you, Stefan. You are really the one doing the work, not me.
Well, we have a wonderful board that you know works over time, and they just make life easy for me.
Yes, yes, yes. You generically, but you guys are doing all the work. But yeah, and I can share experiences, but that's, you know, I don't know how I can help, but these are the ways I'm thinking for now, and I'm always happy to talk about them more.
Well, we have lots of wonderful students that you'd love to hire as you know, all the way from faculty to postdocs and grad students. Keep it up.
Yes, yes, yes. I have been meeting with some of them that you send my way.
Very grateful.